we're into Isaac. We've had the first test, and we're into Isaac Newton. And there are several examples that I have for you. I started with this thing, blocks in tandem on a plane. And we had the block, I think we did the one with no angle. So I'm going to give a class demonstration of the one with an angle. Just bring that one at an angle. And we're going to then, I'm going to do it on the board again. So these problems are really good for really baking in Newton's laws and how to handle them. So I have this whole series of problems that I do and just keep making them more, tweaking them, making them a little bit more complex, building up from the basic problem here where you have that situation and no friction. Okay. So we're still going to stay with no friction. We'll put friction in on Wednesday. But now we're going to take it and put it at an angle. I don't think we did that one. No, we didn't do it. I demonstrated it, but I don't think we did it. Did we? No.
I feel like we did go over it in
We
class.
did? We did?
Okay.
We did that?
Yeah,
Okay.
because I,
Okay, so
I have like a pretty like elaborate diagram in my notes. So
okay, good. So we did this one and we did this one. Yeah.
I'm not sure if I've seen the angle one. Can we repeat the angle one?
Well, I'm not going to redo the same one. I may do it at a different angle. So can you show me your notes, Mikey? Is there a way that you can show me that or no?
yeah, let me just turn on my camera real quick. Hopefully this works. Oh, hello.
Hey, how are you?
Pretty good. Yeah, I don't know if you can see that, but that's what I have in my notes.
Oh yeah. So we did that one. That's okay, we did that one. Yeah. Good, 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 good. So so who was that? Hayek, you were asking. So why don't we do this one? Why don't we do, because the next one I'm going to do is going to be two blocks on two angles. But if you're still kind of shaky on that, we can do this guy, right? Where we do the angle down. How about that? So usually I do those
Sounds
two and
good.
then because then when we put like, two on, that's basically the combination of those two. Because one, it'll be, one block will be an angle up, the other block will be an angle down. So you just kind of put them together. So let's do the angle down. And yeah. Okay, and so yeah, that's right. We did. Thank you, Mikey, for reminding me. And what we saw is that the acceleration got slower, and you can see in the analytical solution where and why it does. And then yeah, when we relax, when we did the limiting cases, made the angle zero, it transformed back to the original solution where we had the flat plane. And so now we're going to see the opposite, right? When we slant it down, the acceleration should be faster. But again, when you make that angle zero, the solution should reduce back to the flat plane. And similarly, the tension got, well, with this guy, the tension got greater. And we saw that. We saw in the analytical solution why. In this case, the tension, as you might imagine, would get smaller. Right. In the case of 9 degrees, there's no tension. They just both fall down in tandem together in free fall. So I found it very helpful back, when I was first learning to go through these things and just kind of repeat them over. And the thing about, I mean, I do this. I don't know. Many people don't do this. Sometimes I would just do these problems over or similar problems because it's kind of like playing an instrument, like it's like doing scales or something. And you kind of bake in the procedure and the I don't know. No, the issue is still we're still kind of honing our problem solving technique in addition to the the physics. And this is what you're going to be looking forward to next semester. A little bit of E&M here. And one of my favorite topics in E&M called Gauss's law. In fact, we'll take a look at Gauss's law at the end of this semester because there is a Gauss's law for gravity that we can apply to when we look at universal law of gravity. Yeah, but these problems give you a whole lot of practice in being able to bake in Newton's laws and get them straight. Okay, so we're going to do the down plane, is it? Okay, we got M1 up here. I think that's the one we were putting up at the top of the plane. M2 down here. Surface is frictionless. I'm going to stick with that. And guys, start there. The system starts from rest. So what is known is the plane angle, theta, and the two masses. That's all you know. So given M1, M2, and theta, we want to determine the tension in the string and so the system tension and the system acceleration. Now, just to review, we got an ideal pulley here. So with an ideal pulley, that means the pulley mass is 0, and we'll give it a radius of r naught. That will, well, it doesn't matter, but if we're not taking into consideration the pulley, then the mass of the pulley, then it just redirects the force. Of course, friction is 0 too if it doesn't have any mass. Well, it doesn't necessarily mean it wouldn't, but whatever, it's ideal, right? So all this does is redirect the force. And so the tension on either side of the pulley is the same, which it's not really the purpose to use a pulley force to change the force, but if it's ideal, you can. As we'll find out, that has to do with something called moment of inertia and of the pulley. But if the moment of inertia is dependent upon the mass, and if the mass is zero, then that means the moment of inertia is zero, and the pulley just redirects force. It doesn't change the force. So because of that, the tensions everywhere are the same. So we've got a tension force here, which I just call T, and a tension force here, which is the same T, which means that this is T here down, and this is T here. Okay. Um, so what are the forces on the object? Here we've got, going from the center of mass, we've got M2G. And here, of course, we've got T. I'm going to bring it on down from the center of mass. Okay. And, excuse this, should be from there somewhere, but make it a bigger box. And we can bring all the forces in metrically. Lopsided head box. So sure, coming in from the center of mass here. And we've got the weight of this guy straight down, so like this. That's M1G. And then we have the tension, the normal force that acts perpendicular to the plane of contact here. Normal force is really acting there, but I can shift it up, project it up, so that, for my coordinate system, it's on par with all the other forces. You can do that as long as you don't change the angle of stretch or, you change the magnitude. Okay, so you saw what happens. I demonstrated the problem. We put the thing on, set up the system, let go, it starts from rest and accelerates. So if we want to know what the magnitude of that acceleration is, the A, it's pointing along the direction of T for that block, so down the plane, like here, that's A, in that direction. And for this block, it's down straight down, A. Now, there's several ways you can think about this. I taught you how I like to think about it the other day. I'm going to go over that real quick again. I'm going to place my axis here. So technically, I'm doing it, I use all the colors in there. So technically, I'm putting my axis, I want to use the same axis to evaluate both objects. So I think of it like this. Put my y-axis here, my positive x-axis down the plane. And then, so it's x, it's y, x. So I just shift the axis over the plane like that, so that the box is still, it has acceleration. Acceleration is a vector. So the magnitude and direction technically should be the same. So the down here is a positive x direction. And this to the right is a positive y direction. Actually, another way you can think about it is, once the thing is moving, whatever is moving, right? So we could think of this as just shifting it along a straight line, I don't know, whatever, like shifting this axis, basically like that. So the thing would be sliding along here with these forces in play, whatever. Same thing I'm doing here. It's just that I'm kind of doing it more realistically because of the manner in which the tension string curves over. Yeah, so I usually do something like that, right? But then to kind of hone in on the objects and make sure I haven't missed anything, make sure that I'm actually understanding what's going on. Third time around, I do a free body diagram for both. Oh, sorry, Mikey, question.
Yeah, can you just go over what was that? I think it's like on the I can't really see what it is. Like on like in the pulley, a minus r theta, is that right? Or not theta, minus
Oh
r.
yeah, or not. I didn't put that the other day. That's just the radius, and it was supposed to be it got kind of big. I was supposed to be drawing an arrow like that, and then put the R naught in between, going from the center to the end. But it was kind of small. But we're not going to be using it anyway, so I don't even really need to talk about it right now if that's throwing you off. Because I don't think I said anything about that the other day.
Okay,
It's
and
just
then
the radius of the.
okay,
Go ahead. Yeah.
sorry, and then MP is equal to 0. Is that what that says?
Yeah,
Correct.
MP is the mass of the pulley, and
Okay.
it's massless. That's what an ideal pulley is. It doesn't have any mass, so there's no friction or mass or anything, moment of inertia associated with the pulley.
Okay.
So I was just kind of putting in kind of the parameters of the ideal pulley. It has a radius, but it's massless, so whatever.
Okay. Thank you.
Yeah. Sorry. Anything else? Anybody?
You want us to put a coordinate system so that the string runs parallel to the x-axis?
Well, it's the way I've usually set it up, but you don't have to set it up that way. But I do think it's important to have some thought process about how your coordinate system is defined. A lot of people like to start with placing coordinate system down here on this one and defining on this block. It doesn't really matter as long as you have something. But I do it this way, so that's what I'm teaching. But a reference frame is kind of personal thing. Like when we are doing free fall motion back in, like let's say you had something falling on the ground, like from a cliff or something. You could like free fall. Well, you could put the axis on the ground, but you could also put the axis, the origin, right, on the ground, so that it's falling through in the negative direction, on positive distance. But you could also put the origin at the point where the object starts, so that it's falling through the negative distance. In the end, if you do it right, you're going to get the same answer for everything because, obviously the coordinate system shouldn't dictate the physical nature of, the physics of the problem because, the universe doesn't know you're putting a coordinate system on it, right? So whatever, how you don't have to do it like this, but so it's not what I want. This is just what I prefer, and I'm just illustrating it for that reason. But if you have some other preference, you can do that. Does that make sense?
Yeah.
And I keep forgetting, like when I don't pin myself, when we talk, it goes back and forth. I kind of looked over some of the videos, and it's kind of annoying when it flips back and forth. So maybe help me to remind. Not your responsibility to remind, but I just pinned it, so now it's going to stay there. But um, yeah. All right, cool. Anything else? Anybody? Great questions. All right, so yeah, let's do the free body diagrams. I'll start with, well, this guy's simple. I'll start with him. It's just so FBD. Just this. M to G down. and tension up. And I always like to put something to let me know where the acceleration is. So the acceleration is positive in the down direction, which we call the positive x direction. For this dude, let's squeeze it in over here, maybe. For this guy, we've got the normal force here. We've got nothing. I'm gonna do it. That's a component. I'm gonna draw. How about that? Gravity is actually, well, yeah. Let's go ahead and take a look at this guy. So if, and you can, we did this a couple of times. I'm just going to write it down. But if this is the plane angle, theta, then theta is also this angle. You can work that out for yourselves again if you need to. So the only force I need to resolve on this is M1G. I just realized I'm gonna go back and I need to assign a different lab, not the one that I assigned, just so I don't forget about it, so no one starts it. Let me just do that real quick. This is the 4th lab that I assigned, not the 3rd lab. Put it in different order. So close this out and publish that. Oh no, that's the homework, sorry. Triple force will be the next one. Yeah, so I like to try to keep my free body diagram a little bit clean. And so here I'm going to have a component along this direction. That's going to be mg cosine theta. The cosine now is along the y direction. And then mg sine theta, there's going to be a component of gravity along the same direction as the tension now. Before, when I had the thing the other way, it was the opposite direction of the tension, which was retarding the motion, right? It was keeping the it was taking away from the tension, which was why it slowed it down. But here you can see in the physics of Newton's laws why the acceleration gets larger when you quantitatively why it gets larger when you bend the when you bring the angle forward like that, because now you have two forces in the same direction. They're adding with one another, the two forces in the direction of the acceleration. One is the tension, but the other is a component of gravity. And we'll see that pan out when we apply the forces, the sum of the forces. But I like to have that kind of somewhat analyzed before I come over here, because I like to take my Newton's second law directly from it's the purpose of the free body diagram is to clear everything out, get it clear as to what forces are causing what type of motion. So here, opposite the normal force, that was the same as before last time. That's mg cosine theta there. But then I'm going to have a mg sine theta down the plane as long along with a tension force down the plane. So this guy is T, and I'm just gonna, you know what, that's getting really messy over there. So I should have just done it over here someplace. A free body diagram, and this would be mass 2, mass 1. So normal force, okay, now we got tension straight down. And we've got mg sine theta down. So that's what I'm talking about. And remember, the acceleration is still along, this is the x direction, this is the positive y direction. And, you know, maybe put a unit vector, that's probably the best thing, it's the most appropriate thing. Those are variable j, that direction. Yeah. And yes, the acceleration is parallel to the x direction. So ax, I guess, and then ay, keep that in mind, ay is 0. As the object moves down the plane, it doesn't accelerate or even move along what we've defined as the y direction. Now, I said this earlier, I'll say it again. In general, with physics, whenever you set up your coordinate system, you always, the idea is that you want to have one of your coordinate directions parallel to the acceleration of the system. If you don't do that, generally you complicate the problem needlessly, because you will then have to write Newton's second law, the motion side, the acceleration side, the change in motion side. You'd have to break the motion into its components as opposed to just the forces. This way, acceleration will always be along a coordinate direction, so it will not have any vector components in your system of equations, only your forces will. And that way, it's usually easier, because generally there will be some forces, because you can have all kinds, you only have one acceleration, right, in each direction, but you can have various forces along a particular direction that give rise to that one acceleration in that direction. So once you choose your coordinate axes in such a way that each component of the acceleration is along one coordinate direction, and in the simple motion like this, when I say components, like this is linear motion. So the motion itself is just inherently linear. But like if you have parabolic motion, like it's not inherently linear, right? Like well, I guess it is in that case, because the acceleration is just vertically. I don't know. I guess there could be some kind of motion, and generally all the motion we do this semester will be such that the acceleration will we'll have one acceleration. The total acceleration of the system can be described as in, like, we're not going to be, well, there's one case where we'll do acceleration where something is moving in a circle, but will be a special case where there's There's no linear component of acceleration. So there's no problems we do this semester where you actually have two components of acceleration. So it's convenient that we can set up our coordinate system so that one of our coordinate axes is along the direction of that acceleration. If you then set up the coordinate system so that's not the case, generally speaking, there will at least be one force that will not be along that coordinate system, so that you have to resolve it, like I've done here with gravity. And therefore, you would then have trigonometric components, sines and cosines, on both sides of the equation. And the problem is that it's very difficult to uncouple either the acceleration or the tension, whatever the forces you want, in doing that. And you've done it needlessly, because if you have changed it like that, so basically here with blocks on the plane, the convention is to, as opposed to having the axis so that the x-axis is parallel to ground, which we could, if we did that, gravity would then be okay. It would be straight along the ground, but then the normal force and the tension would be at angles, which you'd have to resolve them. But also, the acceleration then would have an angle in the x and y direction. So you'd have systems of equations where there's, in Newton's second law, net force equals ma. Well, it would be along the x direction, net force equals ma cosine whatever, and in the y direction, ma sine whatever, or whatever it is. But then you're going to have signs on the other side, and it just becomes a mess. And in the end, you could do it, find a way to do it. You do it right, you're going to get the same answer. But why make yourself have all that trouble when you could just do it the way I'm showing you here, or some equivalent to that? So that's the general reason why we do that. We always try to set up a problem so that the acceleration is along the coordinate direction, and therefore we don't have to resolve it into any components. Any questions about that before I proceed here? All right, so let's address this block of information, right? We're gonna look at both of these equations, apply Newton's laws appropriately for each one, each block, and then we're gonna have a system of equations that we'll solve. Now, when we do have the pulley, that'll be a third, because we can apply Newton's rotational laws of motion to the pulley, and we'll have a set of equations from each thing that we set up and solve. And I'm just showing you basic algebraic ways of solving it, but for some of you advanced mathematicians there, you can actually solve, when you set up the system, you can solve it with matrices. In fact, for those of you who've had linear algebra already, maybe some of you don't have to take it, but in physics majors or math majors, or I think who else, maybe some engineering type people have to take, you get elective. That's one of the things you do. You do circuit problems, you can do that, or you can do law problems where you have a bunch of blocks and tackles and stuff. Because like, this is a simple problem, but a realistic problem, you might have like 3 pulleys and 7 masters or something in a block and tackle situation, and multiples, yeah. And so the easiest thing is, once you still have to apply Newton's laws, but then when we start to do the algebraic manipulation, you could actually set up a matrix, right? And just, once you have it system set up, just put those numbers in, punch a button, and it kicks out all the unknowns. I don't teach that here because, it's kind of I don't want to say advanced. It's not advanced if you know it, right? But we don't really do that difficult problems like that. Because once you understand the physics, then you understand the physics. Doing a problem like that, it's really about, might be like civil engineers, might be that if your civil engineering statics class, I think they're going to have problems like that. If any civil engineers in the room, or or higher level physics courses, maybe they do stuff like that. Or you're civil, yeah. So you're going to be doing, who's that? KM. Who's KM2? Was that Kimberly?
Actually,
Kimberly, is that you?
my abundance proof is civil. So the
Your
proof that I
what?
have, my abundance proof, my abundance in the earth, gold proof
Oh.
is civil. It's actually mining,
Okay.
but when you take the engineering test, they just have a mining engineering mining engineering versus civil, but you still, the same laws apply. So yeah, correct.
Awesome. Awesome. Cool, cool. Yeah, I don't know much about that. I still haven't gone to your website to try to figure out some of your proofs. I will though eventually. Uh, yeah. So how do I find it? Like, is it just look up your name, or you said you had it online somewhere, your proofs?
Yeah, I do. I actually do. I'll send you the link. I don't really want to send it in class because it's kind of like, I just think
Okay.
it's a little bit too much for that. You know what I
Gotcha.
mean?
Yeah,
But
yeah,
I'll make
just
sure
send an
you get
email.
it. Okay.
Appreciate that. Thank you. Where was I? Yeah, so let's get to it. So we're gonna apply to that guy, we're gonna apply to this guy, and then we're gonna have our system. All right. We'll do this guy first. Doesn't matter. Well, let's do this one first. So the second law along the x direction, the first law along the y direction. Let's do the first law first. So net force in the y direction of this guy equals 0. So we get normal force up because it's make it positive. This guy's down minus mg cosine theta equals 0. So gives us that normal force equals mg cosine theta. Same result as last time. So we're good. That's all we need with that now. But when we do friction on Wednesday, then we're going to need that because that is associated with friction. The x direction, the second law. So net force in the x direction equals mass 1 times a x, but it's the same acceleration, so I don't put that. And I've got the two forces. Now they're parallel, so they would have the same sign. I'm calling that the positive direction, so that I write the acceleration positive. So that guy we get mg equation 5. So yeah, mg sine theta plus t equals m1a. If you go back the last time when the thing was tilted up, the mg sine theta was pointed up the plane. So we had that equation t minus mg sine theta, which was basically we were subtracting a term from the tension, and that slows the acceleration down. Here, we're adding a term to the tension, so logically that means that the acceleration would be greater. Sorry, less. What? Yeah, the acceleration is greater, so I'm just had a brain fart. Tension is less, acceleration greater. But we still have two unknowns, right? We technically total of three unknowns: normal force, tension, and acceleration, and we only have two independent equations. So if you didn't know already, which you should because we've done a problem like this, that the physics is leading you through the problem. It's saying, you always need to be equally determined if you look at step 6 of the problem solving technique that I've outlined, right? So where's my other equation come from? That's what you should ask yourself. Well, you're systematically going through evaluating all the physics of the problem, and you've only looked at one object yet. You still got two other objects here. That guy is 0 because it's out. It's ideal. So the other thing is here. So then, you apply Newton's laws to that guy, and that then should give you your other system, your other equation to be equally determined. Same number of equations as unknowns. So when you look at that, again, it's the second law because it's accelerating. And you want to write it so that the acceleration is positive. So you write the largest force with a positive. And how do you know it's larger? Because M2G has got to be larger because it's accelerating in the direction of M2G. Otherwise, it would accelerate up, or it wouldn't. If the forces were equal, it could move, but it would just move at a constant velocity. So we have M2, Newton's second law, net force equals M2A, so that M2G minus T equals M2A. And there you have it. That's my ladder, system here. two equations, two unknowns. Yeah. So this is what steps 1 through 6 should look like for a problem like this. And I know I haven't put them all in the categories, but systematically in my mind, that's how I'm going through. So at step 6, the equations over here, you decide, put a little mental energy into like, how am I going to solve this? Want to set up a matrix and solve it? Go for it. For you brilliant folks out there who are into that. If you want to do it the old school method, then you can do a simple algebraic manipulation. And when I'm doing a little trig algebra trick, I'll show you little tricks, when you go through, as I go through it, that you might take advantage of. I see a positive t here and a minus t here. So as opposed to solving one equation specifically for t or a as sum to the other, here I can just add the two equations. If I add the two equations, it eliminates t, and then I have one unknown as a, and then I can just solve for a. Then I take that a and put it back into either one of these, and I get an analytical solution for t. Now, once you get one value, like you get a numerical, like, because here I don't think I gave you any numerical values. We can just use the same ones we used the other day. I don't remember what they were. You can tell me, just to put it in to show. But I like to get the analytics, unless you're on a test and you got a time issue. Once I get the acceleration, I can take that value and put it back into either one of these equations to get the value, the numerical value for t. For the purpose of illustration and physics and teaching and stuff like that, I'm going to do the analytical solutions for both a and t. So it takes a little bit more time. But then what I really want to show you is what we've talked about. I want to, again, symmetry. Symmetry is the theme of the course. So I want to show you how this solution reduces back to the zero plane solution. And when we put in friction, same thing. It's going to be even more complicated solution. But when you relax the coefficient of friction to 0, when you relax the angle to 0, no matter how crazy complicated the situation starts to look, if you did it right, it reduces back to kind of the baseline problem that we started with, which was a frictionless plane at no angle with blocks in tandem. And again, that kind of logic, for those of you who are going to go on and do great things and get into research and, maybe solving theorems and things like that, there's no answer manual in the universe. So when you get on the cutting edge of cutting edge research, there's nobody to check to whether you got it right or not. So how do you do it? How do you test like this? You test the symmetry, right? Test. How do you test? Well, you test the symmetry of your solution with things that you know, right? So if you come up with some newfangled thing, some of y'all discover, the source of dark energy, then somehow it's got to explain the thing that no theory has yet explained. But somewhere in there, there's got to be some symmetry. There's probably going to be some symmetry somewhere that if you relax that thing, that equation reduces all the way back to some conventional equation that we've already been looking at. So I just wanted to get you in the habit of doing that. I call it theory work requirements. Okay. All right. Cool. Go with that. Awesome. So let's get it. So we add equations 5 and 7. So like I said, the tension goes out, plus this, so that's going to be M2G plus mg sine theta. On the other side, I've got m1a plus m2a. Now, what you can see from equation 8 is that g cancels factors out that side and a factors out this side. So over here we got g times m2 plus, I forgot, this is an m1 here. Wherever there's a sine theta, there's got to be an m1 because that's the thing that was on the angle. I forgot to put that in. Okay. So M1 sine theta equals A times M1 plus M2. So when we solve for A, we have that the acceleration is equal to G times this ratio of mass, M2 plus M1 sine theta over the total inertia of the system, M1 plus M2. That's a symmetry that we see every time. Every time we see that happening. And let's evaluate this quickly. Compare this to the solution we did with the bending it up. There was a minus sign here. So you can clearly see that the accelerate, whenever the angle is zero, sine of zero is zero, so that whole term goes to zero. So we're back to that original solution, which was just M2 over M1 plus M2. But here, when I bend it down, because this term, mg sine theta, is now helping tension, it ultimately manifests as a plus term in the acceleration. So all that just, those kinds of things feel nice. It's like all this logic and sensibility, when you look at different parts of the system, it all matches up and everything is, ties up neatly and makes sense. That's how you study, right? That's how, because this really isn't just about trying to do some algebraic manipulation of an equation to get a number, right? Like it's about trying to understand what this mathematics is trying to tell you about why this system is behaving this way and why it changes its behavior based on some tweak that you make to the system. If you can get to the point where you can start to see that and visualize that and understand that, that's where you start to really, and it's not just with physics, it's with anything really, but for those of you who are not, you're going to be finished with physics when you do this course, you're not going to go on, but we've got a lot of programmers in the class, right? And I think you feel me, right? Like if you guys know more about programming than I do, but the better programmers mean they're more efficient programmers, and more efficient programmers. What makes you, if you're not just natural, how can you get better at it? Well, it's understanding how the relationships of systems and how they work, and basically using your understanding, physical phenomena, mathematical phenomena, mathematical uh, uh, relationships, and programming those efficiently within the program. So kind of understanding that how the math is explaining, is justifying this, you start to see these things maybe mimic patterns, mimic themselves, some equivalent of Newton's laws, some data or something. I don't know, but like the universe is all connected, right? So if you begin to see those things, then you can begin to program them more efficiently, right? And this is a good opportunity. This is one of the reasons that they're making you take physics. It's not just to understand and learn these concepts, but to understand why things do what they do and how the mathematics and the concepts are showing that, how it's a language to show you that. So that's why I like to actually write out, but I'm a physicist, right? So, but doing the analytical solutions as opposed to just getting the numbers and moving on is a way of kind of facilitating that awareness. That's what I'm trying to say. So, like I said, if we had numbers, we could put it in there, get the acceleration, and we could just take the number, put it in here, solve this thing for t, and we got t. Fine. But I'm going to now take the analytical solution and plug it back here, and take the effort to do the algebra, so that I get an analytical solution for t, and then evaluate that solution comparatively to the lesser, the previous problems that we've done. So let's do that. I'm gonna go ahead and erase this now. Well, I guess we could do a number. just to see what the normal force and stuff is. Can anyone tell me, do you remember what numbers we had for these masses the other day? Anybody? Guess I have them here, huh?
Honestly, I'm not
Wait a
sure if we assigned any values. Either that or I'm just missing it in my notes.
Okay. You know
Yeah,
what,
so
let's just at least, maybe I didn't do that because I was kind of, I think I was a little bit behind the other day. So I'll do that right here. Let me just measure this stuff. And, you know, it's not going to be exactly, the numbers won't fit exactly what this thing is because this is not a frictionless surface, right? Probably close to it, but not frictionless. So acceleration probably would have been a little bit faster than what this is going to show anyway, but still, you know, that's 62 grams, and this guy is, oh yeah, 62 64. I think I did it for, maybe we didn't do it for the angle problem, but I remember those numbers now. I just forgot which ones. This is 64. So M1 was 64. Do it over here. M1 is 0.064 kilogram. Oh yeah, because Kimberly was asking me why we had to convert. You don't have, well, in this case, yeah, I don't think you have to convert. I'm going to do it anyway because that's just, I think it's good practice because we're going to be in it. But in this case, it wouldn't matter. You could just put in the grams because the mass stuff cancels out. That's why. But yeah, I remember we did. I think that was for one of them we did. So M1 equals 0.062 kilograms, and M2 is 0.064 kilograms. So it's just a plug in the angle. I think we said the angle was 5 degrees. So I'll make it 5 degrees here. Theta is 5 degrees. But now that you have the numbers, you can just plug those in and compare them to all the three situations, right? Compare them to the angle 0, angle, you know, up, and then angle down, and show that the the values of the accelerations and tensions increase or decrease consistent with what your intuition might expect. So let me crank out this acceleration here. So 5 degrees, so 5 sine M1 is 0.062 times plus M2 0.064 plus the 2, the combination 0.062 enter 0.0 divided by times 9.81. Yeah, I remember something like that. So this is 5.40 meters per second squared. And it was 5 something, a little bit less than that before. Yeah, cool. I'm curious, does anyone have use HP for your calculators, or do you all have the Texas Instrument type calculators in modality?
I was gonna ask you about that.
Yeah, why were you going to ask me, Kimberly?
Yeah, because I don't know which one. Which one should I get? I need a new one because I noticed that when I was in Wally, I was like, the software is not going to work for this, for what they're asking for precision. I need a calculator. So, which one do you recommend?
You know what? It's really a matter of preference. You see this calculator right here? This is a classic HP 15C. I bought this calculator in 1983 when I was a sophomore in college. I've had this calculator all those years, and it has never broken down. I've probably changed the battery 7 times. I don't think they make the physical one anymore, but you can buy a virtual one. Actually, I probably wouldn't buy this version anymore because you could get like a graphing cap. But I like HP, and the reason is because it's really just a matter of preference. I'm not going to say one is better than the other. It's just one what fits your sensibility. So I went for years with undiagnosed issues like dyslexic type issues. I didn't find out that I had these things until I was teaching in my 30s. But from grade school on, I had all kinds of issues with math and I didn't know it, like back then it's different. Like it's back in the 70s, right? 70s and early 80s in the Carolinas. So all kinds of other things were going on back there that I don't want to get into. But I thought I had a math problem. I was, like I went through school with having some, issue with not being able to do math. Ultimately, I began to suspect, like, there was something going on. But even back then, like they didn't have these things. I mean, they weren't out. Like you didn't have diagnosis of dyslexia and things like that back then. That people didn't. I don't know whether they didn't know it or they didn't talk about it. I don't know. But what I found, luckily for me, is that for some reason, I don't know why went with HP. I think I had some Texas Instrument and I just needed a new calculator and I didn't know much about HP. And it's kind of like HP with before, because remember the Apple computer came out in 84. So Apple products and how good they were, none of that was around, like that. It took a couple of years before that, probably by 1987 or so, that they started to get that reputation. Just in it. So the point is that the best devices out there were HPs. They were more expensive though. But I decided because I think one of my professors had like a graphing calculator. So I went and checked it out and I got the thing. They were really popular at the time. But it turns out that HP has something they call reverse logic. So you don't put the numbers in the computer like you do with Texas Instruments. With Texas Instruments, you have to do you have to be very specific about the what is it called, the PEMDAS, parentheses, exponents, whatever that thing stands for. You have to do that and for me that's a freaking nightmare. Like I'm always going to miss something. I'm going to miss a parentheses or a minus sign or whatever, and I just it's a nightmare. And so that's why I was having difficulty on tests. A lot of times it would just be careless errors that I wouldn't catch. That and the fact that I didn't have the technique. But when I got the Texas, so you see how I just worked out this thing, this without writing it down? That is not who I am. I can't do that, like normally. But with an HP calculator, I can do it because it's a kind of, you have to read in their manual what reverse logic is, but you're putting the data in kind of like a what do you call those old school data things that uh, adding computer, they're not computers, but adding machine type things that accountants used to use, like in the movies back in the 40s and 50s. It's kind of like that. So you kind of start at the back and you can basically calculate through as you go through without having to put in parentheses. Now you're still basically kind of using PEMDAS, but you're not using it explicitly. It's kind of like an implicit thing. And so that and the fact that these are also programmable calculators, you can program them. And it has a kind of numeric programming thing. And just the point is that all of that stuff fit the way that I think naturally. So I was really lucky that I was able to find it because it really significantly reduced my careless errors on tests and work. And also it caused me to be able to work faster. So I've never, once I started with HP, I never went back to Texas Instrument ever. And I never will. So that's the main difference for me, is that reverse logic basically saved my life. Right. So maybe give it a try. I don't know. And by the way, I guess I tell you, there's a really cheap way you can try before you spend your money. If you go, like they have there's a virtual version of this classic HP 15C. And I think you can, if you search, you could probably find it free. So you might, play around with that, find it, download if you have an iPad or something, download it to a device and just see if you like it before you buy. Because this is, they still sell those because they were so good and so popular, but there's much more advanced HP calculators that you could find if you want to purchase. But I'm sure they probably still have virtual versions of them, of any of their calculators. See if I can find this.
No, I actually was already leaning towards HP Prime, so I'm gonna just rock with that now because I need an advanced calculator to be able to like whatever I need to download on my laptop. I really need to really see the data. This is like, how do we even know if these people are telling the truth nowadays? So I think that I'm gonna just rock with the HP. I thought that was a great recommendation because I think I'm gonna just get the HP Prime. I don't like Texas Instrument. I just don't like it.
What? Yeah. Yeah, well, you're preaching to the choir on that one. Oh, I had a free trial and it expired. But like you can see the calculator in the background. Like this is kind of so it's basically the same calculator, but obviously the software version is like 12, 10 or 15 times faster than this old school thing. And it's a digital calculator, so it's really cool. So yeah. Yeah, so that's what I would
Yeah, because
recommend. I
in
would
my
definitely.
other project, I need to take considerations from different mathematicians. So I need to really, really look at the data. So I think I am going to try this HP Prime. Actually, because they don't give you a lot of choices, for like the graph ones. So I
Oh
thought
yeah.
that was great. Yeah, I think I'm gonna try that HP Prime. That way I can see the actual data. And if I need to blow it up on my computer, whatever I need to do.
The HP Prime is a graphing calculator. Huh?
Yes.
Oh, cool. Awesome. Yeah. Well, tell me, once you get it, let me know what you think about it.
Okay. Sure.
Does the Prime do three-dimensional graphing? Like conic sections and things like that? Do you know?
I'm sure it does everything that the one you have does, and it also you can graph with it. So it'll probably take me about 90 days just to learn how to use everything on it. I'm not gonna lie, that's just what comes with the territory. But
Yeah.
then when you have it, you have it.
Yeah.
So.
That is true. Like once you get acclimated to a tool like that, it's like it becomes invaluable. And even though that's kind of what that calculator has become for me, which is why I never got rid of it. It just becomes invaluable. That's awesome. Yeah, let me know. Give me an update on that once you get it. Yeah. So what was that number? 5.04 something. I lost it. So, but I think it was something like that. 5.04 something meters per second squared. So let's get the analytical solution for T. I guess we got 10 minutes before the break. Go ahead and knock this out. So I'm going to take this A. I'm going to this is the simpler solution, I think. So I'm going to put it back in here and then solve it out for T. And then we should see the T should be less than it was in the previous examples, both previous examples. So when I take the M2G on the other side and multiply through the minus sign, I'm going to have T is equal to M2G minus M2A, right? Let's stick the A over here. So, and I'm just going to go ahead and multiply the minus M2 through each term. So I'm going to have minus M2 squared minus M1 M2 sine theta over M1 plus M2. And I'm just going to go ahead, that would have been a G here, but I got a G on that term. I'm just going to factor out of everything. And so I've got G M2 over 1 times all that. But now I've got to get the common denominator between M1 and M2. So that's multiplying this thing by M1 plus M2 over M1 plus M2, which will kick out another 2 terms. So T is equal to G, still be outside. And the denominator of everything will have M1 plus M2. And the 2 terms I get from here are going to be M2 squared plus M1 M2. Then minus M2 squared, then minus M1 M2 sine of theta. These guys cancel. I can factor out an M1 M2 from this term and this term. So that's going to give me T equals G, and then I'm going to have an M1 times M2 that I factored out over M1 plus M2, and that leaves 1, because when I factor out that, I have 1. Here I have a minus sine theta. So that leaves 1 minus sine theta. That's the form that I like it, because you can clearly see from that guy the symmetry, clearly. Just like before. When theta is 0, that term goes out and I'm back to the flat solution. But if you compare it to the solution where I put the plane up, there was a plus sign there. There was a 1 plus sine theta in that term. So this is showing you that, you're multiplying this original flat tension with a number, because remember it's less than 1, right? Because you're adding 1, like this number here is going to be a number less than 1. So when you're adding a number less than 1, the whole thing is greater than 1. So this result is greater than the original flat surface guy, which it should be, right? You had it flat, then you put it up, the tension got greater. Now you got it flat, you put it down, the tension should get less than that original, and it does. Because now this number is always going to be a number between 0 and 1, because you're subtracting a number between 0 and 1 from 1. So then you're multiplying that guy, by this original, 0 angle tension, it's going to be less than that. So again, that's the kind of thing I like to do, right? To once I get a solution, because it just really makes me feel like I know what I'm doing. All right. Oh, Mikey, yeah.
Could you go over how you got the, like, in equation 12, how you got m sub 2 squared?
Yeah. So that I did skip some steps. You might have to practice that a little bit, but where are we here now? So you got this equation, right? That's just manipulating this thing around, right?
I think so.
From 7. Okay, well,
11.
so all right, no, it's all right. It's all right. Trust me, dude. When I was doing this, I had to do it over and over until I got it. So it's just been years of doing this. I'm not this good at algebra. So I take the M2G over here, and it's going to be minus T M2A minus 2G, right?
Okay. Yeah.
Then I multiply through this minus sign, and it flips it. So it's going to be M positive M2G minus M2A. So that's how I got this from here.
Okay. Yeah, I got that.
Now I take this A and plug it in here. So I'm going to have M2 times all of this.
Oh, I see it. Yeah, it's like M2 times like M2 plus M sub 1 sine
Yes.
theta. And then
Yes, and there's a minus sign there, so that's how the minus sign is also in there.
oh yeah.
And I've got a G here and a G here, So this is like 2 or 3 steps between here and here, where or maybe between, I don't know, here and here, whatever. I see I'm going to have a G there, so I'm going to take it out. Now, the reason I've done this thing so many, like I do these problems every semester, like this is what I mean, like why I kind of comparing it to playing an instrument, because everybody has a certain talent, right? So some people might be better at algebra, some people not. But just think about, I don't know if any of you played sports or you play an instrument or something. No matter how talented, like Kobe Bryant or a really good example that they used to play up a lot was Larry Bird, right? Doesn't matter how talented you are, right? If you want to be really good or the best at something, you got to take that thing and just practice over and over and over and over again until it just becomes a part of who you are. So that's actually what I've done with this over the years. And so there's certain things that I'm expecting to see. Like I can see it before, like 2 or 3 steps ahead. And that's really helpful because I'm not just relying on my gut, my inherent talent or lack thereof of whatever math or the physics. It starts to be reinforced, and it's hard to explain. But I get the same feeling whenever I'm doing something artistic, like learning a new song on my guitar and I have to practice, or writing a song or something. You have the initial inspiration and then you put it out, but then somehow when you practice it over and over again, something happens. I don't know what it is. It just becomes artistic. That's the only word I have for it. And there is an element of that to this, that you begin to have your own sensibility about how I mean, you got some mathematicians and like, theoreticians and stuff, like, you start to kind of make it your own, and you start to kind of see things that maybe are unique to your sensibilities, and then you do it a certain way that's specific to the way to you. It's like you look at The Voice, right? They talk about you interpreting someone else's song and making it on. Everything is like that, and science is like that. So that's what's happening here, is why so yeah, so that's a long thing, just to kind of a little soapbox for that. But that said, I just don't want you to be intimidated because I'm doing this way. Like, you just have to kind of find the way that you like to do it. And because I've done it a lot, I've already seen certain things that I like that jump out at me. So I write it a certain way, and do it a certain way. And there's certain things that I'm expecting, um, based on, like if I'm doing a very new problem, one that I haven't done before that's similar to this, then I can, again, I can expecting certain symmetries, and it just helps. It helps, and just as opposed to just relying on just the raw mathematics, or um, unless that just is the way that you work, or you lean toward that. So that's what I was anticipating. I multiplied through there, took out the G, and now I have to find the denominator. So there's a couple steps missing between this point and this point. And that is that when you find a common denominator, or you have to find a common denominator, and one of the easiest things to do when you have something like this, where one of the denominators is 1, is you just multiply that whole term by 1, the number 1, because remember, when you multiply something by 1, it doesn't change the value. But in this case, 1 is in the form of m1 plus 2 over m1 plus 2. So I just did that in my head. So if I'm multiplying m2 over 1 times m1 plus quantity m1 plus 2 over quantity m1 plus 2, 1 plus m1 plus 2 is m1 plus 2. m2 times m1 plus 2 is m2 squared plus m1 plus m2 plus m1 times m2. See that?
I'm thinking about it. Hold up. I think that's where I got confused, because I couldn't tell if there was like a plus sign like in between the M1 and M2
Yeah.
and
Sorry.
equation 13.
Yeah. That one?
No, like in between like M1 and M2. Like I thought like there was like a plus, no, like right above that.
Oh, here?
Yeah, I thought there was something in
Mhm.
between there.
No, those are multiplied. That's m1 times m2.
Okay. Yeah, I think I'm trying to, I don't know. I'm horrible with mental math. Like I have to do it like on my own, just like free write it out. Like I'm not gonna lie, like I can't even see it in my head. Like
Okay, that
I'm gonna be honest. Like I don't like, but that's just how I am. Like I just like I need to like write everything down like and play with it before I actually like
that's
truly get
fair. I
so
I actually usually do that, but I got a board that's actually too small. And so sometimes with these things, I do take some shortcuts, but it's just because I don't want to get it too messy and have to write too small and then run out of space and have to erase that, that's why. So let me just since you asked, and it's fair because I'm not sure I did that the other day. I'm gonna just start right here and erase that, start right here, and put in the other 2 or 3 steps.
okay.
Or how many
Also,
are?
I just like I just written it down. Like I got it now. So yeah,
Oh,
I
you
think
do?
that yeah, like it was just like as soon as I see it on paper, just like instantly makes sense. But like I can't like I don't really have like a great ability to do it all in my head. So that's just how I
Okay,
am.
well, no worries. Well, we're going into break. I'll just since I've erased ourselves, going to do it. I'll go ahead and do it. And for because somebody else might have the same question and may not readily see it, so I just do it. So I started here, solved this equation for for so basically this was minus t is equal to m2a minus m2g, right? That's just taking the m2 on the other side, then multiplying through the minus sign, I get this. Now I'm going to substitute a into here, into that term. So that's t is equal to m2a, 2g. I gotta turn this thing out in here. Minus, and this is going to be m2 times quantity, m2 plus m1 sine theta over m1 plus m2. Okay, so then that becomes m2g. Oh, and there's a g here. Sorry, I'm putting the g on the outside. I forgot it. It's right there. So that becomes minus m2 squared minus m1 sine, well, minus m1 m2 sine theta over m1 plus m2, all that times g. Well, factoring out the g, I have m2 over 1, plus and a minus is a minus, m2, am I doing that right? I'm not actually. That might have been something that threw you off. I should have probably kept it like this. Or can I? Yeah, that might have thrown you off. That might have been something that threw you off. If I take that, if I write that minus sign out like that, I should put that in parentheses and make that plus. That might have been something. I didn't. It's not wrong in the end because I kept it, but that might have been an issue of confusion. M1 plus M2.
Yeah, that was a bit confusing because I wasn't sure exactly where I got like that minus sign from. Uh, I guess like equation.
Yeah,
Where was
I
it?
think it was
B
I think
C.
it was on 13. Yeah, I think it was
Yeah,
on
yeah, yeah.
13.
13.
Yeah,
Was it 13?
sorry about that. I think it was. Yeah, sorry about that. Yeah, that could have thrown you off a little bit. So now when I find the common denominator, that other step that I skipped was this. G is equal to m2 over 1. And so this is m1 plus m2 over m1 plus m2 quantity minus, and then all this other stuff. I'm just going to put it like that and then put it in parentheses. So now I'm going to multiply. So I can add them, right? Because they both have common denominators, m1 plus m2. And then I just have to translate that minus sign through and then multiply through here. And so that was the last equation I had before, or the one before the last. So T equals G times M2 times M2 is M2 squared, then plus M1 M2 and then minus M oh, I dropped the square term here, so then minus M2 squared, and then minus plus is minus M1 M2 sine theta all over M1 plus M2. So that guy cancels that guy. And then I'm gonna bring it back over here. So that guy. Yeah, I was terrible at this too, still not the best, but I want you to be encouraged, just practice and you get better at it. And so, yeah, so that's M1, M2 minus M1, M2 and theta over M1 plus M2. So I'll just do this in 2 steps too, because this is a little weird to see how it works. So I can factor out an M1, M2 from there. So I get M1, M2, then 1 minus sine theta over M1, M1 plus M2. So I could keep it like that. But since the numerator is just a product, I can just take it out because then I can write it like, with kind of showing the symmetry that I like to call it. M1, M2 over M1 plus M2 times 1 minus sine theta. Because writing it like that clearly shows, when you compare it to the previous problems, show how it reduces back to those original, those earlier problems we did. Okay, all good?
Yeah, I followed along. That makes sense. Thank you.
Yep. All right, I think it's break time. Need to get a bite. So what time is it? Yeah, okay, let's take 20 minutes today, maybe a little longer. Actually, before you go, just as a working break, if we take longer, but set up the next problem. The next problem we're gonna put them both on the incline. So it's gonna be this guy, and then we're gonna move on. So I'll do something like this, where we have 2 angles and 2 blocks on the angle. So so 1 is here, 2 is here. This is theta 1, and this is theta 2. They're in tandem. Again, ideal pulley, so the pulley is out of the question. So it definitely will, it's gonna, well, it depends on the angles, right? It could go either way, depending on whether theta 2 is larger than theta 1 or whatever. For now, the nice thing about Newton's laws is it doesn't matter. Even if you assume that it's gonna accelerate down this way, if you choose the wrong way and don't make any mistakes, then you just get a negative acceleration, which means it's actually going the other way. So that's the problem we're going to do next. Let's assume, so we're on the same page, that it's actually going the same way down the plane. M2 is accelerating down the plane and M1 is accelerating up the plane. And see if you can give it a shot. Start working it. And we'll come back and we'll work that problem and get the analytical solution for both A and T for that one. And yeah.
Gamble.
Yes.
I want to ask is so when we have two separate bodies of mass in a single problem, and you know how you said to set the coordinate system so that the acceleration or that the force runs parallel to the x-axis.
Yes.
Um, so we're only supposed to use that coordinate system or that XY plane for both bodies.
Yes. Yes. Good question. And it's the same, again, that thing that I taught about shifting the coordinate system over the axis, it works for this as well. So let's say that we have this as the y-axis, and then the positive x-axis for block one is up the plane. Okay. Well, if they have the same acceleration, then technically they should be moving in the same direction. Now, I know it doesn't look like it because one is whatever, but you can make it do that mathematically. And this is how. I establish my coordinate system like this, right? And so then just shift it over the plane. When I get to this, center of mass, now my y-axis is pointing like that, and my x-axis is pointing down the plane. If you treat it like that, then mathematically it works out. Works out. So
Thank you.
that's why I like to do that. Yeah. Yeah. Good question. Anything else?
And then you said to use like the same masses and angles as the previous examples, right?
Well, I have to give you an angle for this one. Let's make it let's do something like if I made that 5 degrees, if I make this larger than 5, yeah, so let's make this let's make theta 2 like I guess I gotta work out it. Sometimes you can design a problem that's not realistic. So yeah, that means that the distance would have to be, because I didn't specify that. So if that's 5, I guess it could be, but it would have to be really steep and short. But it could be long, right? It could be really long, and then this thing is yeah. So it wouldn't really look like if I made this angle larger than 5, it actually would have to look something more like that. Would have to be something like that. So this is not drawn to scale, so don't worry about that. But it would have to look more something like that, where this could be 5, where this theta could be 5, and this could be something like 12. That looks like it's more like even 30 or something like that. But yeah, so let's do something like, but it would mean that the lengths of the planes are not the same. That's the only, and since I didn't establish any length there, then, so let's make theta 2 10. Yeah, 10 degrees. Theta 1 is 5 degrees, and theta 2 is 10 degrees. And so this is an exaggeration, but it would be more something like this, is how it would actually look. All right.
And then same masses, right? Just to make sure, like.
Yeah, same
Okay.
masses. Yeah.
Cool.
Yeah. Awesome. Awesome. All right. Might come back about 5 after. So go make it a working break. You take a few minutes, but then just go ahead and start setting this up, because we will finish this one in class. Okay. I can make this nice for you. Here. All right, so I'll try to draw it a little bit to scale, make a really nice long ramp here for the one. And then we're going to drop this off rather steeply for the other. And I don't know, it's probably more than 10 degrees, but you get the point. So if there's no friction, well, you know, it could go either way. It depends on the angle. Actually, maximizing and minimizing the function. This is a good thing to you can minimize and see, you know, where it would go at the critical point where, you know, what angle you would need to have such that it stopped and went back the other way. I'm not going to do that to you, but you could probably get a optimization problem out of this. But so this is theta 1 here. And this is, we'll make a difference. So that's M1. It's theta 2, M2. And we got the pulley here. I think I need to make that black so I have plenty of colors in this guy. All right. Well, again, as I mentioned to Armand, I'm going to make my axes so that their x-axis is parallel to axis for both objects. Let me do keep the axis black. Seven image. So yeah, positive y up, positive x is down for 2 and along the up direction for 1. Gravity straight down on each one. Here, M1G. Here, M2G. Normal force here. I'm going to call that N1. Normal force here. N2. Now, the accelerations and the tensions are the same because it's an ideal pulley, so we don't have that to worry about. Deal. which means that we don't have to call it a tension 1 here, it's just a tension T. And we know it's on the pulley there. I like to draw it in anyway, even though we're not going to be using it in here, just to remind me of the third law. Now tension here, straight back. Now it's a little, don't want to get too messy, but this is theta 1 here, and theta 2 is here. By now, you should know that project back, I get mg cos along the x direction, sorry, the y direction, mg sine along the x direction for both cosine along the y, sine along the x. So I'm just going to not, I'm just going to jump down to the free body diagrams for M1. That's going to give me normal force here, tension there, mg. Well, maybe I should put it there so you can see it. Mg sine the plane is down. Mg sine. Mg cos theta is here. M1. It's here. Like I project this guy back. That's Mg, actually M1 G cos. And then I project this guy up to here, and that's Mg and 1G sine. Got to put the subscript on here. So this is M1. This is M1. Now again, third time I'm saying it. In this case, because this angle is greater and the mass is greater, I know it's going to go down that direction. But if I had made M1, the theta 1 greater than theta 2, it's possible, particularly since the masses are very close, it's possible that it could have gone M1 down the plane as opposed to up the plane. But you don't have to worry about that. Like, you just make a mathematical choice. Just choose. I'm going to choose A up the plane for block 1 and down the plane for block 2. If I then write my equations of motion that's consistent with that, if my original choice was wrong, the mathematics will tell me if I don't make another error. I'll just get a negative acceleration, which just tells me that I chose the actual wrong direction and it's actually in the opposite direction of my choice. So it still gives you the right answer. Same thing for block 2. I'm going to have, but here, the cosine theta the sine theta is in the same direction, right, as the motion. So here, M2 sine theta is down the plane in the same direction as acceleration, and M2 cos theta is still along the negative y direction. So the free body diagram from this guy is normal force M2, mg, m1g sine theta, and I forgot to put the subscript on the theta 2. That's theta 2, and this is theta 1, and that's theta 1. And then this is tension, and this guy is m2g cosine theta 2. I'm going to apply the normal force to both objects and do it like that. Start with equation 1, or do the normal force first. So again, acceleration here is up the plane, that's A, and here it's down the plane like that. Okay. So no, I guess AX, no acceleration along the Y direction, AY equals 0. So applying the first law along the Y direction, in net force Y equals 0. So I get normal force N1 minus M1 G cosine theta 1 equals 0. So that N1 equals M1G cosine theta 1. And that's my first solution. Box it in. I'm skipping the steps here, going to the same thing here. The Y direction is here now, right? Again, first law. Was 0 for 2. And we get plot 2, plot 1. And that's F2Y. And Y. So similar thing, right? N2 minus M2 G cos theta 2 is 0, so that N2 equals M2 G cos theta 2. Now I'll go to the X direction for both. Here, it's the second law up the plane. But I've got, so block 2, block 1 again. We'll make this equation 7 then. So the net force in the X direction, for 1 in the X direction is M1A. So that's going to give us, so T is in the same direction as acceleration. M1 G sine theta is opposite direction. So minus M1 G sine theta 1 equals M1A. And again, you're seeing those two unknowns there. I can't go any further because I'm undetermined. So I'd have to go to the block 2, the X direction here. So T and M2, that should be 2. M2 G sine theta are in the same direction. So that net force M2X equals M2A. So what we have now there has to be the same sign. So T plus M2 G sine theta 2 equals M2A. Again, unknowns T and A. But so now that's my system. That's step 6. I'm done. And my path is to solve equation 8 and 10 simultaneously, get the A and plug it back into either one of those. Now here, I'm not so lucky because my T is positive in both cases now, right? Yeah. So, um, what I could do is just multiply duh, I made a mistake. I don't know what's going on with me. Sorry. The tension force is here. That's going to be a problem. Tension's not down, it's back up the other. Sorry. My bad. I had this. The tension force is back up the other direction. Sorry. I'm sorry. T is that way because it's connected here. So I can see that's going to give me a problem. I'll make another. Well, thank goodness I caught it. Yeah. So this equation is wrong. Now I have to change it. T is opposite direction of A. So just like when it was hanging down, it was, was hanging straight down, it was M2G minus T. Here is M2G sine theta 2 minus T because M2G is in the same direction as A. We're writing A as a positive acceleration. So I don't know what happened. That was just a huge brain fart. All right. So this is wrong. It should be M2G sine of theta 2 minus T is equal to M to A. Now that's better. So again, A and T are the same, are the unknowns. So I can still do that little trick where I add equations 10 and 8 because T and minus 2 are T and minus T. So A has T and this has minus T. So when I add them, I will eliminate T. Speaking of T, let me go pour my water here. My T. Different kind of T. Oh, God. Different kind of T. Okay, A plus 10. That's going to be positive M2G sine theta 2. These cancel the T's, and then a minus M1G sine theta 1. And that's going to be equal to M1A plus M2A. Similarly, we can factor out a G from the left and the A from the right. Then, dividing through by M1, M2, we get that A is going to be equal to G times this ratio of masses. M and angles, M2 sine theta 2 minus M1 sine theta 1 over M1 plus M2. And you can play around with that a little bit, right? You can see that to get back to the last situation, I've got to make, if I make theta 2, 0, wait, this is 2 here. Actually, when the situation before was when theta 2 was 90 degrees, right? That this scenario, theta 2 is 9 degrees, right? So when sine of 90 is 1, sine of 90 is 1, so this term just becomes M2, and we're back to the solution, the problem we just did. M2 minus M1 sine theta is the thing. And you can go through and work that out and, see those things. And, do that for all the angles, and it'll work out. It'll work out. When we throw friction in on Wednesday, we're going to see that there's going to be a coefficient of friction, a factor, not a factor that's going to pop up here. So it'll be something like M1 mu sine theta 1, meaning friction retarding the motion back down the plane there. And, for that guy too, but like when we just have one angle, see that. So yeah, it just gets more and more complicated. And then when we put the pulley in, there's going to be another term in. I mean, it just gets more complicated, right? But you start here being able to work these guys out, then it, when you get to that, you'll be able to handle it. Should just work up. Yeah, we can put in and see what the numbers are for the here. So I think before we do the attention, yeah, we got 40 minutes, 50 minutes. So what did I say? You can put the values over here somewhere. Theta 2 is 10 degrees. Theta 1 is 5.0 degrees. M2 was largest, that was 64, 0.064 kilograms. And M1 was 0.062 kilograms. Now, I have no idea how this acceleration is going to rate compared to the others. But I think the last one we got was 5.4, I think, before. I mean, I have no idea. There's no way to know. I just picked some numbers, and so who knows? But at least we know the ballpark of where it should be, right? Actually, I guess it should be much less than 5. Now I'm thinking about it, because you don't have the whole weight pulling it down, right? You had the mg minus whatever, but now you got mg sine theta. So the sine theta makes it even more, like the fact that so it should be less than 5.40 with the same number, slightly less. How much less? How much ever sine theta 2 diminishes this term. That much less. Because that's the only thing that's different from the equation before. Sine of, I can start there. So that was 10 degrees. Sine, and M2 is 60.064. 0.64. I think it reduces it quite a bit, because it goes from 0.06 to 0.01. I did that right. Theta 2 is 10 degrees. And M2 is 0.64, I think 0.064. Right? Yeah, okay, so then let's just keep going. So 5, and 1 is 0.062 minus plus, and then 0.064, 0.062 plus divided 9.31. Oh, you know what? I think I forgot to multiply by. Did I forget to multiply by 9.81 last time? It would have made it larger. Something happened here. Something's not right. Yeah, 0.4, 0.44. I don't think it's. Yeah, I think I did something wrong. Unless the other one was wrong. Let's do that again. So we have M1, which is actually, I'm going to go back and calculate that other one again. I might have made a mistake on that. So the other one was, the same thing. I just didn't have a sine theta 2 there. So that was, yeah, I think, I mean, that is a pretty high acceleration. I think I did something wrong before. I don't know what. For all that talking I was doing, my HP didn't help me out very much. Let me help myself. But here I'm getting A to be equal to, you want to go with 3 significant digits, then yeah, 0.445 meters per second squared. Maybe that had just reduced it that much. It could be. Could be. I don't really have an intuition for that. But I'm gonna just calculate that thing again. It could be, actually. Because it, like I said, it decreased it quite a bit by multiplying by that sine of that angle. So here, with this angle being 90 degrees, you just have M2 minus M1, whatever we derived it for. So in that case, we've got 5 degrees sine, and M1 is 0.062 times, okay, subtracting it from M1, which is 0.064. And then dividing it by 0.062 plus divided by, and then times 9.81. Actually, no. Yeah, I got 5. Actually, I got 4.5. Maybe I switched the numbers around. Let's do it again. Got 4.56 that time. I thought it was 5.40, unless I'm thinking of something else. But I'm doing the one where I think the one we just did was this. Oh, that's right, because that was the solution. That's right. Yeah. Nah, this solution, because it's plus here, and before it was minus. Yeah, so this solution was this guy, which we did the other day. And that was the answer we got. So yeah, okay, got it. So when it's like that, that acceleration was okay. So that wasn't a mistake. That is what we got before. It was that acceleration was 4.56 meters per second squared. This one that we just did, that's the one we just did. That guy was 5.40. And now we're seeing this, and look how much it decreased it. So I'm pretty confident that's correct. Yeah, it decreases it, right? And yeah. So it starts off very slow, and then it's almost at that critical point, actually. It's almost at that critical point. And again, I might do the problem because I did write up a solution for that optimization stuff we did a couple weeks ago. I haven't posted yet. I'll post it probably. I got a couple other things I want to do to it. But I guess we're assuming the acceleration is constant. I think the equation to maximize so we want to find the tension in the rope such that the such that you want to find the angle such that the tension is a minimum. Or the angle of tension is a minimum whenever both angles are zero. Maybe that's not the thing. What about the acceleration? Find an angle such that the acceleration is a minimum, which would be zero. But there's two different angles, so I guess holding one constant, we could do it. I don't know. I have to think about that. I think that's a typical. Yeah, maybe with one fixed. I don't know. Okay, any questions? Questions about this acceleration here? Then it just gets a little bit algebraic. We then have to take this A and plug it back into either 10 or 8. And honestly, it doesn't really make a difference. The algebra is going to be the same for either, and you get the same solution either way you go. Whenever we do consider the tension, the pulley though, this will be like a T1 and this will be a T2. And so there'll be two different tensions that you have to solve for. There's three unknowns. But we would have another equation, the equation of Newton's laws for that, which involve moment of inertia and torque and stuff. But that's a few weeks off. But yeah. I'm gonna go ahead and do it. I'll choose stick it in here. Since I wouldn't have to manipulate minus sign, I can just take this guy on the other side and put A in. So starting from equation 8, And I guess I don't need all that anymore, so I'm going to erase that if that's good, so I have room to work. I'm just checking in. Everybody can hear me, right? Sometimes I haven't
Yes,
heard anybody.
Professor.
Pete. Okay, cool. All right. Yeah. So any questions about the acceleration, what I did there to get that? And I'm confident, like that's was a little bit off-putting initially, but comparing it back to the two, like, yeah, it's probably because, like there's some angle that where the thing wouldn't move at all, right? So the acceleration is getting so smaller and smaller. And, you know, I don't know, I was just guessing at the angles, trying to gauge it intuitively. Um, but yeah, I guess it's pretty balanced. Almost you can tweak it and find the balance point. So the acceleration is going to decrease as you get closer to that balance point. I mean, obviously, if mass two here were the same masses and it's close, then the balance angle point should be the same. Like if this is 5 degrees, it won't move. So I've just kind of come off of that a little bit but this is a little bit heavier. So, you can kind of gauge the intuition for yourself. So it does make sense once you start to think of it that way, that the acceleration wouldn't be too high given those set of initial conditions. Yeah. I think I'm going to need all of that board. So I'm going to go ahead and erase this. If that's, I guess you can always look back at it. So these are the kinds of problems. I don't think they're gonna have anything like this in your Wiley homework. I'm not, they might, but I doubt it. But these problems like these are in the chapter, in the actual chapter of the book. They're gonna have a few like this and even some more like it. I mean, they might have something like, but probably not this long for the Wiley, but definitely in the back of the book. So it's worth kind of maybe studying and doing some problems in the chapter as well. All right, so I'm going to go this route, and I'm going to say, so from equation 8, we'll keep the numbering going, so we keep the order. So I call that equation 13. And then 14, we're going to go solve this for t. So t is equal to m1a. Actually, I'm going to write it like this. M1g sine theta 1 plus m1a. Now, when I take 12, I'm going to take 12 and stick it into 14. So 12 into 14, just because I don't want to make a mistake. And also I'm going to be a little bit more transparent than I was last time. Because I did make a mistake last time, but it just didn't affect me because I guess I kind of made 2 mistakes, whatever. But just with that minus sign thing. So this is going to be t is equal to m1 g sine theta 1 plus m1, and then I'm going to have m1 plus m2, and then m2 sine theta 2 minus m1 sine theta 1, times g. The g is there, it's right here. So it's over the whole thing. Check it out. Got g here, I'm factoring the g out of everything. By the way, for you programmers, like if you're doing like any of those, I'm assuming these are the equations they're using when you any kind of like in games and things like that to make it more realistic. You're actually programming these equations in the gaming stuff, sci-fi movies and stuff. That's why when you go to a sci-fi movie, like a space movie or something, and you stay after the credits, it's like a gazillion people. The credits roll for like 20 minutes or something like that, and a lot of the programmers and producers like they're staying in the audience to see their names and stuff. It's why, because it takes like tons of people, you know, to program that stuff. This is the equations that they're programming. Um, so some of you programmers out there, I want to make you laugh. When I was an undergrad, we had to do a senior research project, and my senior research project. Now, mind you, back then, even though the Apple computer came out in '84, the whole time that I was in school, the whole 4 years, when you program, you were still using, I don't even know what they call them. Like we had like a mainframe computer that we had to go and we would like, and they had the cards and stuff. And the language that I chose that I had was no, I wish, even older than Pascal and Cobalt, Kimberly. Our language was Fortran. That's what I was, the official, the language that we use in my class. We programmed with Fortran. And yeah, you had to do the cards. You had to wait for your time. Oh my God, it was like a nightmare for me. I actually kind of like programming, but I didn't like having to waiting all the people and stuff. And um, I don't know, but I tried to do a little. I didn't really get it finished. I actually have it here. Actually, this is it. Uh, Computer simulation of shepherding moon phenomena of the Saturn ring system. Yeah, I tried to. I didn't actually even get to the programming really. I set up the type of um, programming tools and stuff that how you would do it. I never got to actually programming it. But I'd actually try to revisit that at some point. Shepherding moon phenomenon. This is rather difficult task. I've forgotten what the shepherding moon phenomenon is. The planet. That makes sense. The Fortran supplied random function. Algorithm. A simple algorithm utilizing the Fortran supplied random function. This algorithm was constructed fairly simply, but once done, it proved not to be random enough. Forward. Let me talk about the time question. Oh, shepherding phenomenon. Creating curve gaps. That's why we miss out. Diameter. Yeah, vaguely remember now. So, there was a one of the first satellites we shot off was I was in the ninth grade. It was Voyager 1. We did Voyager 1 and Voyager 2. Voyager 1 went out, and Voyager 2, out toward the outer planets. Voyager 2 went to the sun and ultimately flew into the sun. Voyager 1 went up when I was 13. I was in the ninth grade. This was 79, I believe. And it went out and kind of swooped around all the different planets. By the time I was a junior or senior in high school, it was at that Voyager 1 had reached Saturn and had sent back data. And basically what they saw is that the moons around the planet, they bobbed along. There was like this perturbation and they couldn't figure out why. And they think basically gravitational anomalies, because there's a whole bunch of junk going around, right? You got the rings are actually dust particles and things, and then the moons are a bit larger, but then you might have moons close together. And so basically the gravity, like with our moon, there's nothing there but the moon. So whatever the actually will show with that thing that I erased from the board, the Gauss's law, that we can determine the gravitational force, and it's an elliptical orbit. So you could estimate a circular orbit, but everywhere that the moon is, the gravitational field is the same because it's just one. It's if you assume from the center of the Earth, it's like a sphere, and it's not a circular orbit, but it's a very slight elliptical. But if you could approximate that. For the first approximation is a circular orbit, and the gravitational force is the same. But you can imagine that. What if you're at a place where the gravitational force is not the same, right? It's kind of like when you get air pressure that's not the same in an airplane, right? You get the bumps and the fluctuations. Well, if you've got something moving along in a gravitational field, and the gravitational field is, you got really strong, it's like that could also happen, right? You even know the lensing, you might have heard of the lensing effect with very large gravitational fields where it's like it bends space-time so much so that if you're going through it, it's like, presumably it would be like riding in an air where there's a lot of high and low pressures. You're riding through space where there's a lot of high and low gravitational fields, it's going to be hard to keep a stable orbit, right? So they speculated that because of the dust particles and maybe a closer moon by this moon that they saw, like the gravitation, like very far away, it looks like they're moving around, smoothly. But when you get up close, they're doing all kinds of things in those rings, right? Because there's a lot of junk going. It's, huge gravitational fields of the planet. It's just all kinds of stuff going on, right? So you kind of have like well, you know how the moon affects our oceans and you get the tides going back and forth. Well, you could think of all those dust particles as like an ocean themselves, right? Like, but then you got the moons, they got all these different gravitational, bunch of different moons and the gravity of the planet. It could cause those things to fluctuate and flow, you know, kind of like it would be, I wouldn't want to call it tides, but it would have some, again, symmetry, right? It would have some kind of analogous effect. Um, so that's a much more general thing. The shepherding moon phenomenon specifically takes that idea and looks at individual moons, not just everything in that space, but the individual moons. And so it's a really complex thing. And I had read about it and I thought I might try to mimic something. I don't know. Like I didn't get to be able to actually work it out and show that in the program, but it was an effort toward that. Uh, yeah, yeah. So I don't know how I got off on that tangent, but I guess I'm just taking a break before I do this and giving you all a chance to uh, giving you all a chance to balance before we finish this out. Hmm. So I'm going to go through the same process. I always do that just so it helps me keep from making mistakes. Like how I caught that mistake before with that other thing, right? That's why I kind of go, that something was off and I wasn't going to be able to eliminate T like I would like to. And that's how I caught that mistake. So I'm going to factor the G out first out of both terms. Leaving N1, M1 sine theta 1 plus, now I'm going to multiply through the M1 to both terms, plus M1, M2 sine theta 2 minus M1 sine theta, M1 times M1 is sine M1 squared sine theta 1. And this is over M1 plus M2, and this guy is over 1. Common denominator is going to be M1 plus M2. So here, this is G times M1, I'll write it out, and then times M1 plus M2 over M1 plus M2, right? That's 1, plus just this thing. So M1, M2 sine theta 2 minus M1 squared sine theta 1 over M1 plus M2. Oh. Drop the 1 here. There's a theta 1 there. Now I need to multiply. I'm going to get 2 terms out of this. And the denominator is just going to be M1 plus M2. So I can add everything. All right. So denominator, M1 plus M2. The 2 terms here are going to be M1 times M1 is M1 squared sine theta 1. M2 times M1 is plus M1 M2 sine theta 1. I still have these 2 terms, plus M1 M2 sine theta 2, and a minus M1 squared sine theta 1. M1 squared sine theta 1 minus M1 squared sine theta 1. That's out. M1 times M2 sine theta 1 plus M1 times M2 sine theta 2. I can factor out the M1, M2. Almost done. T equals G times factoring out the M1, M1, M2 over M1 plus M2. Now I'm left with sine theta 1 plus sine theta 2, and it's a factor. So sine theta 1 plus sine theta 2. And I could just take it out, right? I could just go ahead and take the whole thing out, and that's my solution. You write it down a little bit more. Well, yeah. So again, we can see the symmetry. If you relate it to this guy, it's probably closer to this guy than to this guy, because when they're like that, they're kind of opposing one another, so the tension should get greater. Then, you know, I mean, definitely it should be, it makes sense that there should be a plus here, not a minus sign, because, you know, they're opposing one another. So when this situation we had plus, and this situation was the minus, and the tension got less. So we're kind of back to this, but with less of an angle. And also the tension is going to be less here than it was here, right? Because here it's pulling straight down, but when I put it on an angle, it should be, you know, not pulling as much. And you can actually see it. I don't know if you remember, but this solution was actually, I start remembering. This solution right here was actually, T was equal to G times M1, M2 over M1 plus M2 times 1 plus sine of theta. So I can see that this tension is going to be less than that. Why? Because 1 is greater than sine theta 1. This is going to be a number between 0 and 1. So this whole factor is going to be definitely greater than 1. Now, this could be greater than 1. I don't know. It depends on the angles, but it will always be less than this factor. And everything else is the same. So putting it on, and we saw it, right? We saw that we got a slow, you know, well, that's the acceleration, but still. Yeah. Presumably, if you haven't changed the masses, if the acceleration is less, then the tension should be less. Think about it. When the accelerate, well, that's not true. The acceleration, that's when the acceleration, the tension is a minimum. Like I said, when the acceleration is 0 and it's not moving, but the tension wouldn't be 0 there. Tension would only be 0 when they're both falling straight down. Yeah, so I don't know, you could beat it to death, but I just find it interesting to get these solutions and then just kind of think about them and, you know, compare them back and forth and stuff. And you begin to kind of see things that you didn't see. It stops looking just like a bunch of mathematical mumbo jumbo. And if you're kind of feeling like that, okay, fine. Yeah, I did too. Everybody does, unless you're just some genius, you know. But the more you kind of play around with it, at some point you hit this critical mass, and it's, you know, it's like Neo in the Matrix, right? You can see the language. And so for me, doing these little things like that and kind of preparing, it helped me to get there a little bit more efficiently. And again, you know, I mean, I got to give credit to Isaac Newton, man. I mean, like, it's one thing to do this; it's the one thing it's a whole different ballgame to create it, or discover it, or have it, you know, the realization that this is how the world works. And so the Atwood machine is actually, it's going to be simple now that we've done all this. It's going to be really simple. It's a classic problem, and it's going to be in your book somewhere. But it's basically where this same problem, but with no angles, right? Like it's straight up and down. So you get like a pulley, and you hang the two masses on it, and one is greater than the other. Again, assume ideal pulley. Eventually, we'll have to deal with that, but ideal pulley. So it's just redirecting the force. That's all. And you know, if M2 is greater than M1, and it's ideal pulley, then the acceleration is going to be down here. So M2 greater than M1, which ours slightly was. So it's going to rotate down. So the question is, find the system acceleration and the system tension. What are they? See if you can give me a little pop quiz. You got 10 minutes. See if you can apply Newton's laws to this system and give me an analytical solution or whatever, or either just the values for acceleration and tension of this system. Now, quickly, again, everything we did could be done the same way, right? Like, so I can take, well, here, I guess you would have to kind of say, you know, if you put your axis here, and this thing is going accelerating up along the positive y-axis. But the way I think about it is I just flip the axis on the other side. So then for this guy, down is the positive y-axis. So I could still kind of say that they're moving along the same direction, right? So here, this would be x over here, and this would be x over here. Anyway, x doesn't matter, right? Because only the forces are going to be along the y direction. So you just go in and you sum your forces, right? You say, well, I'll get you started, but like here you got M1G down and tension up. And here, M2G down and tension up. But after all of that, this should be a piece of cake. So see if you can do it. See if you can set up the equations right, get the solution, and we can still use those numbers. We can use M2 is 60, M2 is 64 grams, and M1 is 62 grams. And yeah, I guess like you said, you actually wouldn't even have to change it over, do you? You don't have to convert it if you don't want to. So yeah, go ahead and knock that out. See if you can do that in a few minutes. Yeah, this is called the Atwood machine. Mm. 4:26. Give it another minute. All right. Starting here, applying Newton's, it's only the second law to each one, right? Because it's accelerating. So starting with mass 1, net force in the y direction equals M1 A. So which force is greater, T or M1G? Well, if I want to write A as the positive acceleration, it's going to be T. The force in the direction of the acceleration is greater than the force opposing. So this becomes T minus M1G equals M1A. Switch over here, accelerating down. So obviously M2G is greater than T, but for M2. Right? So again, positive acceleration, going in the positive y direction down. So we have M2G minus T equals M1A. And that's it. I told you, it's simpler. It's like lifting weights, right? You lift larger weight or whatever, then you go back to the lighter weight and it feels lighter, right? So two T's, one positive, one negative. You add the equations. And we're going to have T's go out. We got M2G minus M1G equals. So it's going to be M1A plus oh, this is M2, sorry. But then I could well, you just got to write out M1A. Sorry, my left-hand writing is not so good today. M2A. So again, I factor out an A and G on each side, whatever we've been doing that. And we get this guy, that A is equal to G times quantity M2 minus M1 over M1 plus M2. Makes sense. See the symmetry all there, the inertia, divided by the inertia, factor of G, the mass, that stuff goes out. M2 is driving it, M1 is retarding it, hence the minus sign, right? M2 is forcing it down, M1 is kind of dragging along, like we've been seeing all that before. I'm not going to do the, I'll let you put in the numbers if you will, because I want to go ahead and get this out. I want to do the tension before we go out. So I'd have to take, I take this guy and put it back in here, for example, then the M1 comes over. So if I were working on that, then give me some room here. Guess I don't even need this anymore, really. So then putting equation 5 back into 2, and then taking the minus M1G over, the 5 into 2. The T is going to be equal to M1G plus M1 times this thing, which is, get the G out here, it's going to be M2 minus M1 over M1 plus M2. Go a little fast here. I'm going to skip some steps. You can fill them in later. So I think we talked about that several times today. So I think you don't see it quite now. You can figure it out, I think. So equals, well, I know I'm going to have this denominator, M1 plus M2. So I definitely got to multiply this guy. And I'm factoring out the G. So I get two terms here when I multiply. It's going to be an M1 squared plus M1 M2. And then M1 M2 plus M1 M2. And then a minus M1 squared. So that guy goes, and I get two of these. So it becomes T is equal to G times 2 M1 M2 over M1 plus M2. So we keep seeing all this whole factor of stuff, like this thing here, you know, and then it's just always it's some version of that or symmetry is related, you know. And yeah.
But I think I made a mistake. Where'd you get 2 from? Let me see. I thought from equation 2 we saw for T. You scoot over really quick?
Oh yeah, sorry.
Yeah.
It comes out of here. I get 2 of them out. I got M1 times M2 and then M1 times M2. And it comes whenever, well, I skipped a couple steps, but whenever I do that common denominator term here, you're gonna get you get 1 from that. Like it's this M1 times that M2. But then you get another one, this M1 times that M2.
Yeah, but I think. Oh, go ahead. I'm sorry.
No, go ahead. I'm done.
No, I'm listening. I'm sorry. I want to listen. Go ahead.
No, that I was just going to say, yeah, that's it. And then from this other guy, you get, you know, like this. Well, maybe I shouldn't skip it. Let me just, because I could have made a mistake. I don't know.
Because what I'm trying to show you, boss man, is right here from equation 2. Right here from equation 2, we can solve for T. And you know, for simplification, we get a simple T, which I think I left in the chat box. And I think that's T. T is that, right?
Yeah. That's what I was saying. Like once you get A and you have the number, you don't have to do what I'm doing. You can just plug that number in, and T is equal to M1 M1 times
plus M1A plus M1G.
Yeah.
Very I left it in the chat box for you. So that's why but I guess you do it for symmetry. You said you like to take.
Yeah, because I like to see, you know, I like to get it into the, you know, I call it the analytical solution, just because I like to compare it to all this other stuff we did in the physics and stuff, you know. I can't see it as much, you know, even though this is absolutely correct and you will get the right answer. I don't really see the physics as much when I do it like that as the other. But whatever, it's all good. And once you know, right? So then you don't have to do what I'm doing if it doesn't call for that. And but you know, like in class, I like to try to teach all these little subtleties and things like that. But yeah, you're right. You're right with that. You do that.
Yeah, I'm sorry. I didn't mean to cut you off. I had just wanted you to see that. Like you could just from step 1, you could add MG1 and go from right there. Because you know we're on Wiley, and you know it's taking us time. That's why.
Yeah, that's true. On a test, or if you got like push for time, you don't have to do all that stuff that I was doing. Right. Absolutely.
Dr. Gamble, can you show the solution for tension?
Oh yeah, the one I can write it down. So so then T. So doing it like how I put all the steps in here, you got to have a common denominator, and I'm factoring out the G. So I'm going to have an M1 over 1. But then the common denominator, again, is going to be M1 plus M2 over M1 plus M2, right? And so this guy over here is just, you know, plus, and then M1, and, well, so times M2 minus M1 over M1 plus M2. And I've taken the G out, I factored the G out. Okay. So now I want to get the 4 terms out again. T is equal to G times here. And so the denominator is just going to be M1 plus M2. Now here, M1 times M1 is M1 squared. M1 times M2 is plus M1 M2. So that one comes from this term. Now here I get another one, M1 times M2. But then I get the minus M1 squared. And so that goes out, and I'm left with M1, M2 plus M1, M2, 2M1, M2. So putting it with the symmetry of these other ways I've set it up, it's a 2 M1, M2 over M1 plus M2. Is that good? Is that Armand? Is that you? Is that you asking?
Thank
Yeah. Awesome. All right. Today was a good day. I got actually a little bit more than I planned to get done. And I think this is helpful.